Today we're going to continue looking at section 6.5, which is still all about trig equations. So not only are we going to solve trig equations, but now we're going to be looking at it in a specific restriction to its domain. And then we're also going to be bringing back the idea of factoring to help us now solve equations. Okay, so here's our first example. It says to solve the equation 2 sine squared of x minus 3 sine of x plus 1 equals 0. And notice this time I'm giving us a restriction on what x can be. So I'm not asking for us to find every solution. I'm asking for us to find the solutions within one rotation around the unit circle. So if we look at this equation, we don't have sine isolated by itself. And we also have two different types of sines. We have a squared sine and then a sine to the first power. So how are we going to go about solving this? Well, if we ignore the word sine for a second and we just think about it in terms of x, it's the same thing as 2x squared minus 3x plus 1 equals 0. So this is why we're bringing back the idea of factoring to help us solve equations. We're just replacing the x terms with a specific trig function. All right, so because this does not have a GCF, we are going to have to think about factoring where we're going to start with a 2, and then instead of saying x, I'm going to say 2 sine of x. And we're going to have the second factor be just a sine of x. All right, now we're asking ourselves what multiplies to positive 1 but adds to negative 3. Well, the fact that we're multiplying to a positive but adding to a negative means that we're going to be dealing with two negatives. And the nice thing about this, there's only one way to multiply to 1. So if you really quick distribute that back out, notice that 2 sine of x times negative 1 is negative 2 sine of x. Negative 1 times sine of x is negative 1 sine of x. So negative 2 and negative 1, there's my negative 3 sine of x. All right, so now I'm going to take each factor and I'm going to set it equal to 0 to continue solving for sine. So to isolate the sines by itself, notice in this first equation, we're going to have to, we're going to have to add 1. So now we have 2 sine of x equals 1. So then lastly, we'll divide by 2. And so now we're dealing with the sine of x equaling a half. In the other equation, we just have to add 1 to get that sine of x by itself. So sine of x equals 1. And so because we're just looking at one rotation around the unit circle, we can now look at our unit circle that I have here. So let's start with the sine of x equaling a half. Remember, sine is second in our ordered pair. So here's a positive 1/2 second. And over here in the second quadrant, there's 1/2. That's positive. So I know that my two answers for that is going to be when we're at pi over 6 and we're at 5 pi over 6. If I want to know when the sine of x equals 1, once again, we're talking about the second value in our ordered pair. So it's going to be just at one spot up there at pi over 2. And so these would be the three solutions to this equation. I do want to point out that if maybe one of our equations like this sine of x equals 1, had it been like the sine of x equals 4, okay? Remember, when sine of x equals like 4 is not going to be found within our unit circle because remember, our unit circle has a radius of 1. So sometimes we might have an equation that does not give us a solution. So always just think about that in the back of your mind, okay? If it's not a value that's on this unit circle, well, then that's not going to be a value that we can actually solve for x. If we take a look at this next example, we're going to solve the equation that 4 cosine squared of x minus 3 equals 0. Once again, notice that we've got this restriction. We're going to go from 0 to 2 pi, so one full rotation around the unit circle. Well, as we can see, we do not have our cosine isolated by itself, so that's going to be our first step. I'm going to add 3. I'm going to divide by 4. And then we are still not quite done because I need to get the cosine by itself. So I'm going to have to take the square root of both sides. Now remember, when I take the square root, I don't have just one answer. I have 2 answers. I have both a positive and a negative. I can break up this fraction as the square root of 3 divided by the square root of 4, but the square root of 4 is a perfect square, and that turns into 2 in our denominator. So we have the cosine of x equals both positive and negative square root of 3 over 2. So cosine is going to be first in our ordered pair. It can be both positive as well as negative. So that means that there are going to be 4 spots, 4 spots on my unit circle where I'm going to have the cosine as either positive or negative square root of 3 over 2. So that means we're going to have 4 values. We're going to have it at pi over 6, at 5 pi over 6, at 7 pi over 6, and at 11 pi over 6. And so these would be my solutions because they're all within that one restriction of just one rotation around the unit circle. If I look at this example, solve the equation for the sine of x times the tangent of x equals the sine of x. Notice that we do have the same restrictions. I just wrote it a little bit differently. So we're dealing with one rotation around the unit circle. Notice that 0 is included. Notice that the parenthesis here tells us that 2 pi is not included. Okay, so it's a tiny bit different than from the other ones because in the other ones, all the signs were both less than or equal to, but in this case, 2 pi is not being included, but we're still thinking about going around the circle one time. All right, so notice that in this case, we have trig on both sides. And so to help us out with this equation, because there's a sine of x on both the left and the right, I want to get everything to the same side. So I'm going to subtract the sine of x over to this other side here. And so now I have the sine of x times the tangent of x minus the sine of x equaling 0. Because this is still a factoring problem. I have 2 terms and they have something in common. I'm going to factor out the GCF. So the sine of x gets factored out, and that leaves us then with the tangent of x minus 1 in parentheses, and that still equals 0. So now that I've factored everything as much as possible, I'm going to set each factor equal to 0. And the sine of x equals 0, that's already isolated by itself. So let's figure out where are those values. So when sine, which is second, is 0, that would be over here, and that would be over here. Okay, notice that that means that 0 is included, so 0 would be one of my angles. We've got pi, which is within the restrictions, and notice that technically, even though 2 pi hits at sine of x equaling 0, that's not within our restriction, so I can't put 2 pi, so just those 2 values. Over here, I'm going to add 1. And so I want to know, when is the tangent of x equal to 1? Well, remember, if we're looking at our unit circle, tangent is the same thing as sine divided by cosine. And so in order for it to turn into a positive 1, we have to divide by the exact same thing. So where's the exact same thing in our ordered pair? Well, when both our square root of 2 over 2's are positive, or when both our square root of 2's over 2's are negative. So that gives us a value of x over here being at pi over 4 and at 5 pi over 4. Now, the thing about these types of equations, when you have 2 different trig functions, it is going to be important that you are checking to make sure that while they work these values work individually with like the sine of x or with the tangent of x, you do want to make sure that they also work with the other trig equation that was with, or the other trig function that was within your equation. So like 0 and pi, they work with sine, but do they also work with tangent? Okay, so if I really quick go and look at the tangent of x and I plug 0 in for that x value, so the tangent of 0, I want to make sure that I have a true statement here. So if I go over to 0 and I'm thinking about tangent, well, once again, sine divided by cosine, notice that it'd be 0 divided by 1, which is 0. And so that does check out, but had it been, if we were dealing with it like up here at the ordered pair of 0, 1, with it being pi over 2, well, then we would have had 1 divided by 0, and that would have been undefined, and so that value wouldn't have worked with tangent. So you want to be making sure that the values aren't going to turn out undefined for a portion of your equation. So 0 works. If I look at pi, once again, 0 divided by -1 would be 0, so it's okay that tangent of pi is a part of my equation. All right, there is nowhere where sine is going to be undefined. So these values will work out. They are true statements, but it is a good idea to double check because there might be a value that while it works for one portion of your equation, it doesn't work for the other. And so you do want to make sure that you are just thinking about that. I would say pause your screen and try this really quick. Solve the equation that the cosine squared of theta minus 1 equals 0, where you have the restriction from 0 to 2 pi, with 2 pi not being included. So pause and try this really quick. Hopefully you were able to come up with these two solutions that when you moved the 1 over by adding, took the square root, you have both cosine of theta equaling +1 and -1. And so we have two values there, 0 and pi. So that's us solving trig equations in a specific restriction and us factoring to help us solve these equations. So this is what I'd like you to try for homework on page 637, number 39, 42, 45, 48, 49, 60, and 61.